Our lesson for today will be looking at chemistry 1502. We're still busy with reactions, SN2, lesson 104. Let us start. We have looked at some of the properties of SN2, nucleophilic substitution reaction, and we've also looked at a number of reactions. So today I want us to talk about other properties of SN2 reactions, things that you should know based on this type of reaction. Remember that we have SN1 and SN2. So today, one of the concepts I want us to talk about is the configuration, specifically the inversion of configuration. The stereochemistry of the SN2 reaction, you should know that all SN2 reactions proceed with a backside attack of the nucleophile, resulting in inversion of configuration at the stereogenic center. So let's say, for example, one of the most common examples that we use to explain this phenomenon. Let's say we have this substrate, reacting this with a nucleophile. Remember that we know exactly what this represents. We know that most of the nucleophiles, they have lone pairs. By the way, any substance that has a lone pair can act as a nucleophile. And in SN2 reaction, we can have electron-rich nucleophiles with a negative charge or a neutral. We cannot have a nucleophile with a positive charge. Remember that nucleophiles are negative and then electrophiles are positive. So in this case, looking at the inversion of configuration, what will happen is that under SN2 mechanism, remember that SN2 is only one step process or reaction. What happens is that the nucleophile will attack from the back. This is the stereogenic center, by the way. And then at the same time, our leaving group will leave the substrate, and it will leave as a halide ion. To represent the inversion, let us go ahead and also show the transition state, what actually happens, because some of the multiple choice questions, you might find that you are given a reaction and then they say show the transition state. The transition state is whereby we have that bond forming and bond breakage. Remember that the two reactions, they happen simultaneously. As the nucleophile attacks the electrophile, our leaving group also detach itself from the substrate. And you should also know that we have two different types of inversion configuration. The first one is this type. We're just going to explain it in detail. It is partially negative, it is also partially negative. Somehow the two, the nucleophile and the leaving group, they form 180 degrees. The reason why is because remember that according to the nature of charges, negative and negative, they repel each other. That is one of the reasons why the nucleophile will not attack from the front, because that is where the leaving group is located, and it is also partially negative. So if we have a negative charge and also a negative charge, it is not possible for them to actually attract each other. So just to make sure that we write the mechanism correctly, also a pair of electrons will move from the substrate or the bonding between carbon and bromine, it will leave with this as a halide ion. This is just a transition state whereby it all happens, the bonding and the breakage. And we can also say this undergoes hydrolysis reaction. And then after the reaction, we know that we are no longer going to have this, but we are going to have our new substances, which is the product and the leaving group. Our leaving group will definitely be Br with pair of lone pairs and having a negative charge. And then we are going to have our new, let me say the product, we call it the product. This represents the invasion configuration. If you can look at this and this, you can see the difference. Look at the orientation of these two and also look at this. This is the first type of invasion configuration. Let us look at the second one. Second type, it's when we have something like this. Our nucleophile is OH. And then in this case, we know very well that this will be our leaving group. It's a substrate, our nucleophile. What will happen is that the leaving group will have this pair of electrons, and then the nucleophile will attack the electrophile. And in this case, you should note that this represents that the chlorine is in the front and our hydrogen at the back. So in this case, our nucleophile will attack from the back. It cannot attack from the front because we know very well that this is partially negative. And then if our nucleophile is negative and this is also partially negative, it will not be able to attack from the front. So it attacks from the back. Now what happens is that normally, for the sake of explanation, I would say the nucleophile will replace anything that is at the back. In this case, you can see that our hydrogen is at the back. So it means that as it attacks from the back, hydrogen will not share that position with our nucleophile. So it means that our product, we know very well that it will consist of our our halide ion, which is our leaving group, and then we are going to have hydrogen in the front and then our nucleophile at the back. You can go ahead and put on the lone pairs. Now look at this. This is also an invasion. It's another type of invasion configuration. Let us look at the effects of nature of substrate on rate of SN2 reaction. There are those questions whereby they will ask you if it will be possible for the SN2 reaction to take place, or which reaction will take place fastest, or the faster reaction that will actually occur. So you should know that the nature of the substrate plays a very significant role when it comes to the SN2 reaction. Remember, I said we do have different types of alkyl halides. We have primary, secondary, and tertiary. And you should also know that we have the methyl halide. So when you talk about a methyl halide, is it possible for the SN2 reaction to occur on a methyl halide? An example, a methyl halide is when we have a methyl group let me actually try to use a stereochemistry. Remember that when a nucleophile attacks, it always attacks from the opposite direction of the leaving group. So it means that it will attack this direction. Now in this case, for the methyl halide, it's very simple for it to attack because we don't have any hinders. It's just an open space to the electrophile. When I talk about hinders, I'm talking about other carbons. So in this case, it's very simple for the nucleophile to attack the electrophile. So this, it's a methyl halide. So we say the SN2 is very much simple for it to occur. So let's say we have SN2 under primary alkyl halide. Remember primary alkyl halide, it's when we have our halogen bonded with carbon that has bonded with another carbon. Let me actually try to use the stereochemistry. So we have C here, and then we can just write it like this. So we do agree that this will be our stereogenic center, or the carbon that will be attacked by a nucleophile. So as this leaving group leaves our nucleophile, it will be a bit slight difficult to attack our electrophile because of this hinder. Compared to this one, you can see that we don't have anything that hinders this nucleophile. So for the primary, we are going to have a slight difficulty to get to our electrophile, but it is not impossible. It is actually possible for the primary alkyl halide. So for the secondary, suppose we have Br bonded with CH, and then we have CH3, CH3. You can see these are barriers. So it will be possible for the nucleophile to attack, but it will be a bit difficult because these methyl groups will actually hinder the stereogenic center. So for the secondary alkyl halide, it will be a bit difficult compared to the primary. And then when we look at the tertiary alkyl halide, it is impossible, because let's say we have our Br, then we have our carbon which is bonded to 3 other methyl groups, T-butyl bromide. You can see that our nucleophile, from the back, it will be difficult for it to attack the electrophile. So we say that SN2 doesn't occur when we have a secondary alkyl halide as our substrate. And you should know that in terms of the fastest reaction that might take place, we start with the methyl group, and then we go to primary, we go to secondary, we go to tertiary. So this will most likely to occur faster compared to this, and also the primary will occur faster than the secondary. This will take place, SN2 reaction will take place, but it will be slower compared to the primary. So that is what you should know. And then this one will almost be impossible, if not impossible. So that is what you should know when it comes to SN2 reactions. Some SN2 reactions, they react very quickly or very fast compared to the other ones. Some of them, they react very, very slow. And you should know that it depends on few things. Like, I've just covered the substrate, the type of a substrate that we have, the type of alkyl halide we have. Then you should know that other factors is that the better the nucleophile, the faster the rate of SN2 reactions. You should also know that the best nucleophiles are also the best electron donors. Remember that when the nucleophile with a pair of electrons donates electrons to the electrophile or attacking the electrophile with its electrons, the rate at which this happens depends on the nature of the nucleophile. If the nucleophile is good, it can donate electrons, you should know that the reaction will also be very fast. And then obviously if the electrophile is actually poor, it simply means that the reaction will be slow. So it doesn't only depend on the substrate, whether it is a primary, methyl, halide, secondary or tertiary. So let us take a look at very weak. We are going to start with very weak nukes, or let me say nucleophile. So we have the first one of the weak nukes, and then we have, by the way, these are conjugates. If you understand acids and bases, then you'd see that these are conjugates of acids, because we normally say nucleophiles are bases or they are basic. So these are very weak nucleophiles that we have. And then we have weak, which are ROH, HOH, which is water, also nitrate ion. These are weak nukes. Followed by, we can say fair nukes, which is fluorine ion, fluoride ion, chloride ion. You can write them down for the sake of notes with ammonia. So these are fairly fair nukes that we have. And then we have good nucleophiles, which are N3, Br, OH, CH3O. You can see that these nukes are one of the nucleophiles that I've used in most of our examples that we've went through so far. And then we have very good nukes. Also write this down. They are very important because you might find that you will have about 4 reactions whereby when you look at the nucleophiles, one of the reactions has this as the nucleophile, the second one, let's say, has this, the third one has this, and then the fourth one has this, and then they'll ask you which SN2 reaction will likely be the fastest or the slowest, and then you should be able to answer the question by looking at the type of the nucleophile you have, also considering the substrate. Remember that the methyl halide, primary halide, secondary halide, tertiary halide, they also play a significant role when it comes to the rate of the SN2 reaction. Let us discuss the nature of the solvent under SN2 reaction. Now we know that solvent is where we have a substance that other substances, or let me say solutes, they react in or dissolved in. Most of them are aqueous or liquid. So the solvents in which the SN2 reaction takes place also plays a very significant role, and you should know that we have 3 classes of organic solvents. The first one is protic solvents. You should know that protic solvents which contains the OH or the NH2, they slow down the SN2 reaction, meaning that they are not ideal or they are not good for the SN2 reaction. They actually slow the reaction down. The second one is polar aprotic solvents like acetone, these types of solvents, they have a strong dipoles, but those that do not have OH and NH2 within the solvent, you should know that they speed up the SN2 reaction. Sometimes you might find that multiple choice questions, everything is okay, everything it's actually favors the SN2 reaction. I'm talking about all the options, but you'd see that sometimes you are given the reactants, let's say A plus B, your nucleophile and your substrate, and you are given this arrow, and then on top of this arrow it is written the name of the solvent here. It might be acetone or anything that has OH or NH2 within that solvent. You should know that mostly will represent the solvent here, and then you are given the leaving group and the product. You should check this if it speed up the SN2 reaction or it slows the reaction down. So you should also check whether it is polar, aprotic, or it is protic. And then we have non-polar solvents. NP stands for non-polar solvents, like hydrocarbons. You should know that normally the SN2 reaction, they react slowly in those types of solvents. Now, before we close this lesson, you should know that this is not the last lesson. We do have a number of lessons under SN2 reaction, including the practice questions lesson 103.2, which we look at more examples. But for this lesson video, you should know that SN2 normally reacts first when we have substrate as methyl, followed by primary, followed by secondary, and then lastly by tertiary. But we know that in most cases tertiary will almost not be impossible to actually react. And then we have nucleophiles. Good nucleophiles, in most cases, they have a negative charge, or some of them are neutral, do not have a positive nucleophile. Then we have a leaving group. In most cases, a stable leaving group will have a negative charge. And then lastly, our solvent, which will react, must be polar and aprotic. Remember, protic solvents, they slow down the SN2 reaction, and also nonpolar solvents, they slow down the SN2 reaction. That's it for this lesson video. This is Paula SJ. Thank you very much.